Today we're going to discuss a little bit more set theory. So in the last episode we talked about what a set is, what you can do with sets, unions, intersections, that kind of stuff. Today we are going to expand on that a little more. So I want to start off with a concept of the universal set. So a universal set, typically it's denoted U, or maybe it's like, actually maybe I should do my U's like that, like a capital U, or sometimes there's like the double stroke U, but I'm just going to call it U like that, okay? So the universal set is basically the universe that you live in, that you're considering with the other sets. So let's say, so let me write kind of some relation. We can talk about how A is a subset that is not equal to the universal set, and then also B is a subset that is not equal to the universal set. So they kind of exist in this big universal set, so we can draw it like a rectangle maybe. So they kind of live in this universe. So this is my universal set. And let's say A is over here, and then we have B something like this, okay? So now, what I want to think about is, what can we do with this? Well, let's first think about some unions and intersections. If we take A, and if we take the union of A with, let me make that union a little better. We take the union of A and the universal set, what are we going to get? Well, the union is just all the elements that are in either one. And so we're going to actually get the universal set back, because any point in the universal set is going to be part of our union. The intersection, however, so if we intersect this will give us A. And so if we take B intersect the union, we get the union. If we take And so if we take B union the universal set, we also get the universal set back. And if we take B intersect the universal set, we get B back. And so this is generally true for any sets, okay? And we can also think about the empty set. If we take A, if we take the union of A and the empty set, which I'm going to denote it like this. If we take the union of the empty set, which I can't even draw it on there, I'm just going to get A back. But if I take the intersection A intersect the empty set, I'm going to get the empty set, because the intersection is what has to be in both. And since there are no elements in the empty set, we can't get anything back for our intersection, so it's empty. So these are just some very important things that you have to consider. I guess I didn't really need to draw a second set in there, but just to kind of have a better picture. Okay, now I want to discuss the cardinality of sets. So the cardinality basically measures the size. So if we have a set, so let me just do a divider. If we have a set, I don't know, C, which is equal to, I don't know, 1, 3, 8, 16, and then I can have like a 0.5 and A, just some weird random element A, okay? This is just a collection of random things. I have some whole numbers, I have a 1/2 here, I have a variable, just random things. If I take the cardinality, so I'm going to denote the cardinality with like absolute value bars. Sometimes it's also written as like card of C or something like that. There are other notations, but I'm just going to keep the kind of absolute value bars, because that measures, I don't know, I just feel like that's better for this. So the size of this is going to be how many elements there are. It doesn't matter what they are, it's just how many. So if we take 1, 2, 3, 4, 5, 6, that means C has 6 elements. Pretty straightforward, but what if But this is only for finite sets. What if you had something about infinite sets? Like, what is the cardinality of the natural numbers? Well, you may think, okay, well, that's infinite, because there is an infinite amount of natural numbers, right? Okay, cool. How about the real numbers? What's its cardinality? Well, it's going to be infinite as well. But do you agree that there are more real numbers than natural numbers? Because the natural numbers is just maybe 0 if you count 0, but it's 1, 2, 3, 4, it's just all the whole numbers, the positive whole numbers. The real numbers is all of that, but also everything in between. So you can probably think like, okay, well, the real numbers, the size of the real numbers is definitely bigger than the size of the natural numbers. There's definitely a lot more elements in the real numbers than the natural numbers. But they're both infinity. So what does this mean? Well, it means that there are different sizes of infinity. Some infinities are bigger than others. And you may think, oh my god, that's insane. There are a lot of really, really good YouTube videos about this. I think 3 Blue 1 Brown has a video about this if you want to go more in depth. I'm just going to kind of give you the little taste of what's going on. But basically we can classify these types of infinity. So it's very common to denote the natural numbers, the size of the natural numbers, as aleph naught. Aleph is a Hebrew letter. I'm not really that good at drawing it, but something like that. That's okay, I guess. Let me make that a little nicer. I don't know, something like that, and then with the 0 there. This is aleph naught, or aleph 0, whatever you want to say. It's the size of the natural numbers. The size of the real numbers is, I forget, I think it's the continuum or something. Basically, it's a math frac C, so it's like something like that. It's like a weird looking C. I'm really not good at drawing these symbols. So, something like that, like a boxy looking C. Something like that, whatever. And so there's a lot of relationships between these. There are some good Wikipedia articles I can link in the description if you want to learn more. But yeah, there's some really cool things that's involved here. Let's think about the size of the rational numbers. Okay, well, the size of the rational numbers, it seems like it's more than this, right? But it's less than the size of the real numbers, because, you know, between every rational number there's an irrational number. And, you know, the rational numbers contain all of the natural numbers, but then a lot of stuff in between. So you might think, okay, it's between these two. But we have a very clever way of ordering them. And this is due to Georg Cantor. He's kind of the founder of set theory, and he thought of all these really, really wacky ideas. And so I forget if he came up with this or if other people down the line came up with this, but there's the idea of what's the continuum hypothesis. Continuum hypothesis. And basically what it is, it says that there's no set that is between the size of the natural numbers and the real numbers. And you might feel like, well, we just showed the rational numbers, right? Not really. He used a very clever trick where he can order these numbers. So for the natural numbers, there's a very clever order. It's a very trivial order. It's just 1, 2, 3, 4, and so on, right? And you can order them that way. And he called this order, he called it countable. So it is a countable set, or countably infinite is another way to say. With the real numbers, you really can't order them because, like I said, between any real numbers, there's like more real numbers, and you can keep going, and there's going to be more and more and more real numbers. So this is not countable. Instead, this is uncountable. And sorry, I'm kind of making a mess with everything over here, but this is uncountable. The rational numbers, well, you can actually have an order here. So first you can make like a big table, like an infinitely long table. And you can have, let's say, numerators up here and denominators down here. So numerators here, denominators here, because all rational numbers can be written as a fraction. That's their definition. So let's say we have numerators of 1, 2, 3, 4, and 5, and then we have like 1, 2, 3, and so on. So then you can start ordering them. So you'll have 1 over 1, 2 over 1, which is 2, 3 over 1, 4 over 1, 5 over 1, and so on. And then down here we'll have 1 over 2, 2 over 2, so on. And then it keeps going down here just infinitely. And then like off to diagonal. Bro. And you can see, well, like, okay, that's 1, that's 2, 3, these are all the integers. But then you may be like, okay, well, there's a repeat here. 1 over 1, 2 over 2, 3 over 3, and so on. Those are all just equal to 1, so you can cancel those out. There's some like 4 over 2 is equal to 2. I don't have any other examples here. If I went on a little more, I could find some more. But like that's, like, sure there are repeats, but there aren't that many repeats compared to all the other non-repeats here. And so there is a clever way to order the rational numbers. So in fact, the size of the rational numbers is equal to the size of the natural numbers. And so the rational numbers are also countable. So we have the countable example here and a countable example here. And then uncountable, we have the real numbers, but also another example of uncountable numbers is r minus q. And this is the set minus. It's we can also think of this as r minus q, like that, basically taking the whole set of real numbers and then subtracting away the rationals. So these are the irrationals. And R, in a sense, is a universal set for this. And so we're taking the universal set and we're subtracting away a portion of it, and we're left with the irrationals. So that's a little bit of an application here. But the irrationals are not countable because you actually cannot order them in this way. So this is really, really crazy because you may think, okay, so it's probably about half and half. They're half rationals, half irrationals. But in fact, if you compare it, they're basically, compared to the number of irrationals, there are basically 0 rationals. And it's just such a weird thing to think about. And there's a little bit of a Vsauce video on that with like a probability thing. I'll also link that if I find it. Yeah, there's so many cool things with regards to this, and I meant to talk a lot more about other kinds of things in this video, but this video's gone on too long, so I'll leave that for the next one. So thank you guys so much for watching, and I will see you in the next video. Bye guys!